is presented by Dr. Meulenberg of SF-18, and the title is Composite Model for LENR in Linear Defects of a Lattice.
Thank you. This is, I'm going to try to abbreviate this because there's a very interesting talk following. This is sort of a historical view of things that had actually come up in the past and not been ignored, but certainly not recognized, and how they actually come together into a model now. And this model actually, I would have ignored these other papers had I known about, well, I knew about the Synhouse paper, but Ed Storm's model sort of drew this together, and I think it all fits, so I'll be interested in seeing comments on that. There are two things here that are important, showing the historical point. First one was from Schwinger's paper in 1990. I'll go ahead and read the quotation. This representation of the overall probability per unit time as the product of two independent factors may be true enough under the circumstances of hot fusion. But in the very low energy cold fusion, one deals essentially with a single state or wave function, all parts of which are coherent. It is not possible to totally isolate the effects of the electric forces from those of the nuclear forces. This is an important feature, and I think it's one that Ed Storms has appealed to, and it probably offended a lot of us physicists until we thought about it, and finding that Schwinger actually made this comment certainly lends a little support, makes us pause in our views. And then K.P. Sinha in 1999 said he had located charge pairs on hydrogen atoms in the crevices, voids, or linear empty channels of the solid. And the chain of deuterons will have their own spacing in the chain. This is also an important feature of Ed's model, and it gives an alternative to the view that I've had in terms of what is the extended Lotron model. So the problem that Schwinger was facing was how to avoid creating neutrons in the DD fusion. He already knew at that point that there weren't enough neutrons to account for things. And so he was going ahead and looking and seeing how can you account for that. So he didn't know at that time that there also was a deficit of tritium. But he went ahead and proposed a model, to use up some of the nuclear energy before fusion actually occurs. And this was a point that Ed Storms has brought up, and again, physicists say, no, can't do that. But there is validity. Instead of worrying about the potential wells spaced apart in 3 space, now we're actually talking about the possibility of the potentials spaced apart in time and using the energy that way. Okay, so then the results of Schwinger's model is that there is a correlated phonon-induced motion in the deuterium sublattice. You have basically a stimulated emission, but there are no energy levels there. And he specifically talks about this. You have a large displacement of the deuterons, and you're actually getting nonlinearity. And this is also an important feature. The emission-enhanced displacement gives you more emission, which gives you more displacement. So there's a positive feedback mechanism here, which is important. So the question then is, how does the phonon emission alter the motion in there? If you have an increased number of phonons because you're generating them in this nonlinear region, drawing energy just like this, you've seen these perpetual motion machines. Every time it goes by, it has a magnetic kick. And the same thing there is that in this operation where you have this breathing mode, every time you come close enough to the nuclear potential, you in fact are getting a kick and generating phonons in that process. So the high phonon emission gives a local concentration of phonons, which amplifies the motion again. But those phonons then are dissipated, and and you're dissipating nuclear energy through the lattice, but at the same time, you're establishing a much closer relationship between the different deuterons. Okay, so Synhouse in 1999, he was looking at, first thing you have to do is you've got to overcome the Coulomb barrier. So how do you do that? And he came up with the concept out of the semiconductor and the solid state physics that in a distribution, you know you're going to have D plus and D minus. Well, if you're having an electron taken from someplace, it's likely to come from the closest place. So you have D plus, D minus, and now instead of having a Coulomb barrier, you in fact have a Coulomb attraction. You're separated by the lattice spacings, but when you come together, you in fact have this relationship where it's an attractive thing. So you've really abbreviated the Coulomb barrier and greatly enhanced the tunneling probability. Second part is that if you're in a linear defect, you have a sublattice within that defect, and that sublattice is a one-dimensional, not a three-dimensional structure. Three-dimensional structure gives you a very rigid spacing in the lattice. If you're in a one-dimensional case, you don't have that problem, and that becomes very important. Oh, a comment here is in terms of the background. I'm only going to go up to a certain point, but once you get beyond that point, then you have all the consequences. And there are three posters up there, 31, 32, and 33, which shows the consequences of this model and how you end up getting the transmutation, getting what is, I think, an important and novel feature is you're actually getting a scavenging of radioisotopes. So when we're talking about starting up problems, you have radiation and then it disappears. Well, once you have enough generation of the product that you have here, it goes ahead and it actually annihilates the radioactive, or it decay of the radioactive isotopes. So take a look at that and see how this fits in. Okay, so Synhouse Model came up then with this multivariable Hamiltonian. This is very similar to what Peter was talking about, except that it does not include the relativistic effects. The extended Lattice model does include the relativistic effects. But basically, you have the kinetic and potential energy of the electron, its relationship with the lattice. You have the kinetic and potential energy of the deuteron pairs, or the hydrogen pairs, and those pairs end up having a common frequency, and this is done to establish the displaced oscillator. And again, you're having the interaction with the lattice and with the other sublattice components as well. In these equations, the difficulty in trying to do any solution here is that there are basically 7 parameters, and they're not constants, they're variable with different dimensional regimes. And not only are they variable, but they're interdependent. So you really don't have an easy problem trying to solve this. There are 3 regimes you have to worry about. The lattice-dominated regime, where we're talking in the angstrom range. Then you have the sublattice regime, where you're actually bringing these things into the picometer range, and things change. You no longer see the lattice. You're only interacting within the deuterons. And then there's the coalescent regime, where you're in the sub-picometer range, where you're actually having the fusion. And so these equations, to go ahead and solve this, Schwinger went ahead and said, okay, we can go ahead and do this and get the phonons, but it really gets very complicated if you try to get details on that. Okay, so now if we put these models together, we have a linear defect which has a low barrier between the sublattice components, and you have lateral confinement. When you go from a 3-dimensional molecule or atom to a 2-dimensional, your hydrogen ground state drops deeper down. If you're able to, during the oscillations, when they come closer together, then you end up having a even deeper potential well, and that becomes very important. So then, in the model, you have the fixed lattice versus the variable lattice spacing. if you're in the, and this is what Ed Storms kept harping on and beating ahead, you can't do it in the lattice, in the crystal itself. It just doesn't work. And the idea here is that in the lattice you've got this three-dimensional fixation that you don't have in the linear model. If you are able to go ahead and get this oscillation, then Schwinger says you're generating phonons, and that's dissipating the energy to the lattice even before you actually get to the fusion. That becomes an irreversible process. And that's one of the problems, and perhaps one of the tests. Are you actually having a reversible situation, or once you start having an irreversible situation, what happens? It forces things. There's those things that have to be considered. Okay, these are some pictures from Tom Bernard. I thank him for that. And this is, here we're bringing down, now we're over an order of magnitude shrunk from the atomic or the molecular spacings. And what we see is if we look at the electron distribution, we still see, despite that, we see the electrons are spread around, but they're strongly concentrated relative to the molecular hydrogen. The dimensions here are already beginning to shrink into a one-dimensional configuration, simply because you're bringing the protons together. The electrons are being focused in. And as they're being focused in, they spend more time between. And again, Ed's comment was, you have to have an electron in between. How do you do it? Well, here we're actually seeing why you're having an electron spending more time in between. This allows things to shrink dramatically. So what I've actually done is I took Tom's model here and his next model, and I extended it into a linear chain of hydrogen. Well, you can actually call them atoms, but when we have this linear chain, we're now establishing a linear molecule. And the key feature here, the reason that you have a molecule is when you bring the protons together, the energy, the kinetic energy electrons distribute the electrons beyond, and they can't really do the screening. But if you end up with a molecule like this, the electron motion is in this linear region. And so the electron, when it goes out of this region, goes into this region. So you're not losing the electron. Every time you have an electron going out of the range, you have another one coming in. So you're able to maintain a high density, electron density, between the nuclei. And that allows you to go ahead and have much larger dynamics, and with those much larger dynamics and with screening, as you become closer together, this actually rises, and now we're actually able to go ahead and have kilovolt potential well that the electrons are actually focused into. So this is what Akito is able to do with his tetrahedral system, where you are focusing, you're concentrating the electron paths in between the protons, and that gives up enough, builds up enough negative charge that you're no longer focusing or forcing the protons to stay out. So there are several methods of going ahead and allowing this to happen. And the Lochan model is one way to do it. This is another way of doing it. The tetrahedral model is another way. So there are ways around these limitations. And these are the kind of things that we need to talk about in the community, or outside of the community, both, to say, hey, there are ways around these Coulomb barriers. Now, what we have here is in a lattice, we have fixed spacings. And this is an example here of fixed lattice spacings. And you have the oscillations, and these are the longitudinal optical modes where the deuterons are beating together, and they come together, but they can't really come together very close. You've got the lattice barrier, and you've got the forcing, the spacing, which keeps them apart. But if you have a variable lattice spacing, now these are no longer separated. The lattice spacing itself can change. So with no more amplitude in terms of the phonon interactions there, you're now able to bring these much closer together. And you're now able to go ahead and get into a fusion regime. Okay, so basically to come up there, in the present view, we really have a linear defect. That comes out of Synhouse Model, and I argued with him for a long time, didn't believe it, but we ended up doing other things. But that now has come up, and we really have to thank Ed for this, because he brought it from a different viewpoint and is able to emphasize it. And so I said, okay, let's look back at this and see what KP was actually talking about. If you have a host-bound sublattice, you can only go ahead and bring the hydrogen molecule atoms together in pairs. If you have a linear structure, now you're able to have a linear molecule and you can bring them together in groups, and that can be important. Okay, then from Schwinger, we're really talking about the necessity of having a total potential well. And if you go ahead and include that with the one-dimensional sublattice, this gives you a lot to play with. So if we have now the extended Lattice model is a way of getting beneath the fragmentation level. And if you have the linear model and using Schwinger's approach, you're able to go ahead and dissipate nuclear energy before you actually have fusion. So again, you're able to get beneath the fragmentation level. And Schwinger was mainly trying to get rid of the neutrons, but extending his model allows you to go ahead and get rid of, and actually get below the proton fragmentation level as well. Now, one point where we disagree with Ed is that what Schwinger says and what we say is you don't eliminate fragmentation, you simply alter the probability. It's a continuum. You have a probability, it's a very steep hill, but you actually have the possibility of generating still the hot fusion within this process. It's just a low probability, but halfway down, you now have the fragmentation with the protons. So these are all possible, and they fit the data that's been seen. But if you aim for trying to reduce or eliminate, if you try to enhance to show the nuclear products, you're actually going away from cold fusion. Cold fusion tries to eliminate that entirely. So in conclusion, we have then different models of cold fusion are actually converging. We're seeing the common features. We want to go ahead and amplify those common features, solidify them, agree on them, and be able to present that in a coherent picture to the outside world. Thank you.
Questions? Excellent thought. Thank you. Questions, comments?
Well, since my name was taken in vain, I thought I'd make a comment. I really appreciate your putting my model in context, giving it the necessary vocabulary from the physics point of view, and also pointing out the various conflicts between your viewpoint and mine. It's almost impossible to come up with an original idea about theory. Everybody's thought of everything. What I've done is try to triage the various ideas and put them together into a coherent package that has a very definite logical prediction that can be tested. Many of the theories are so amorphous that they can explain anything, and they frequently do. So I've tried to do that, and doing that, it becomes a, what do I call it, a target. And I welcome that. As I say, I don't care if you believe my theory or not, just don't believe anybody else.
Other thoughts or comments?
And do you consider this actually, at this point, pretty close to what you were proposing?
Yes, I would say you're certainly a little over 50%.
Very good. Well, thank you.